Now that we talked about the main types of reaction orders, which describe how a reaction takes place over time, we can now talk about the other factors that affect our rate, which are going to be temperature, the frequency of collisions, the orientation of the molecules, and the activation energy, which is the minimum amount of energy needed for a reaction to take place. First, we're going to really focus on the effects of temperature. Generally, temperature increases, makes the rate increase as well. That has to do with many different things. Generally, it has to do with a higher temperature means faster molecules, more collisions. So in our rate law equation, what is changing is the rate constant. It is temperature dependent, and it's going to increase with temperature. So we can see if we plot the rate constant, this is for a first order reaction versus temperature. Then we see an increase in temperature exponentially increases that rate constant. These rate constant double approximately every 10 degrees Celsius rise. In this image here, we can see in cold water, this reaction, which is the reaction that takes place in a glow stick. You can see that when we have cold water, it's taking longer for that reaction to take place because it's not shining or appearing as bright. Where in hot water, the reaction goes a lot faster, so it's going to, in the same amount of time, be brighter than in cold water. In a bit, we're going to explore this relationship between temperature and rate constant after a little bit more on the other factors. When we're talking about the frequency of collisions, it makes sense that if we have more collisions, we're going to have more reactions. This is based off kinetic molecular theory from the gas phase, but can translate into all the different phases. So molecules need to collide, i.e. interact, in order for a reaction to take place. So if we have more collisions, we're going to have more reactions. So that is why the more molecules we have, the faster the rate. And also that has to do with higher temperature can also be explained to this because we have a higher kinetic energy. So we're going to have more molecules colliding. The frequency of collisions are going to be higher just because they're moving faster. And so just remember that in a chemical reaction, bonds are broken, which takes energy, right? That's an endothermic reaction, and new bonds are formed. So when we have collisions, that has to happen with enough energy to break bonds to get over that bump, which we'll talk about in a future slide. The molecules also, they can't just hit each other with any kind of orientation. If we look at this reaction here where we have a chlorine atom reacting with this molecule to produce chlorine gas and the residual molecule, we need these two chlorines to hit, or if they don't, then they're not actually going to form a bond. So when we have them interacting directly like that, straight on collision with enough energy, then they will break that bond between the chlorine and the molecule it was once bonded with and form a new bond. If that original chlorine here hits the wrong side, well then there's no reaction that's happening, and so it'll just bounce off and a reaction won't take place. So it's important that molecules are properly aligned in the direction that they need to be to form that new bond. So they need to be in the right orientation or direction. The minimum energy that it takes for a reaction to happen is called the activation energy. So we basically need the molecules to collide with enough energy to overcome this energy barrier. So they're going to need to have enough kinetic energy so that way when they collide, they can form this activated complex or a transition state. So what is that? This is this in-between state at the maximum energy level. We'll see on the diagram soon. When we're at the transition state, you're kind of at this in-between from your reactants to your product. you're in this really high energy state. Because as we know, high energy states, they're not very stable. If we think about, electrons being promoted to high energy, they always want to come down to a low stable energy. So this is our transition state. It's not stable. It's really quick. We can't isolate the transition state, but it's that in between your reactants and your products, where you could either go backwards, back down to your reactants, or if you have that enough energy to cross over it, you can now form products. The energy that it takes to get to the transition state, that's also called activation energy. There are plots that can be made that show us kind of visually what's happening within a reaction. So what's actually really cool is these were developed by Henry Eyring. The chemistry department at the U is named after Henry Eyring because he worked here and he helped to develop this transition state theory. So basically what we have here is potential energy versus reaction progress. So initially we're starting off with our reactants, and they have their energy that we've calculated from our thermo chapter. And as we increase the energy, the molecule will behave in such a way that it starts to form products. So if we look at this reaction, basically what's happening is the carbon and nitrogen switch place. And so as we add energy, it starts to bend in such a way that the reactants start to transition. Once we hit this energy maximum, this is our activation energy. When we're at that spot, our reactants have halfway transitioned into our products. So they're in this in-between state. This is that really unstable high energy state. This is our activated complex or our transition state. Once they have enough energy to cross over the barrier, then they go down in energy and settle at wherever their change in energy of the reaction is. So if it's endothermic, it'll end up here. If it's exothermic, it'll end below. Cool. So that helps us to know that this is where our activation energy is and also where our transition state is. It doesn't matter what happens after the reaction, like whether we're endo or exothermic. That doesn't get impacted by our activation energy. That's completely separate. That's just dependent on where our energy of our products happens to lay. But our rate constant actually depends on how big our activation energy is. When we have a really high activation energy, that means it's going to take a lot more energy to cross over. So it's going to be slower. So high activation energy means a lower rate constant, right? If you remember, high rate constant means fast reaction. So these are going to be inversely related. So high activation energy equals a small rate constant, or also a slow reaction, and vice versa. I really like this image. We've seen it before in the gas chapter. It helps to explain how the fraction of molecules changes at different temperature, right? So at lower temperature, the peak is smaller, so it has a smaller kinetic energy. Most of the molecules do, but there's still some that are below and still some that are above. At higher energies, let me change my color. At higher energies, the average is we have a higher kinetic energy, but we have, again, it's a bigger spread. So we're going to have even more molecules with higher kinetic energy and some with lower. So if we plot our kinetic energy like this and then put a line where our activation energy of our reaction is, anything above that line means that those molecules can react, can overgo this transition state, and can form products. So when we're at higher temperatures, we have a bigger amount of molecules that are shaded above that line that are able to have that reaction happen. So this is just saying that all gases have an average kinetic energy, but each individual molecule has its own energy, which will just be somewhere in that plot. And at higher energies, we're going to have, which therefore, because of higher temperatures, we're going to have more molecules that can get over that energy barrier, and our reaction will take place. So here we have 3 different reactions, and they each have their own energy profile. The first part wants us to rank the forward rate constants from smallest to largest, assuming that they all have the same frequency factor. And then we're going to rank the rate constants for the reverse reactions. So take a minute and try to do this on your own. Feel free to pause the video. Okay, so we're first going to look, the activation energy for the first one is 15 kilojoules per mole. For the second one, it is 25. And for this third one, it appears to be 20. Okay, so if we're wanting to rank the rate constants from smallest to largest, well, that's the same thing as going from slowest to fastest. So we know that slower reaction means a higher activation energy. So the one with the highest activation energy is 2, and then 3, and then 1. So for me, it makes most sense to think of things from slowest to fastest rather than smallest to largest K, but do what you need to do. Here it wants to go from slowest to fastest, so again, that's going to be small k to big K, same as before. So we're going to, for the reverse reaction here, let's use a different color. We have, if this was our reactants and these were our products, our activation energy would be 25. For number 2, we would go from negative 15 up to positive 25, so that changes 40 kilojoules. And from here, we would have, starting at a positive number and going up, it looks like 15. So our slowest one is going to have the biggest activation energy. It's still going to be 2. And then 1 is next, and then 3 is going to be the fastest. So now we're going to really start talking about the relationship between our rate constant and temperature. And so Arrhenius came up with this relationship, and remember the plot kind of looked like this, right? Where it was rate constant versus temperature. So he found a relationship. It is an exponential relationship where he said that the rate constant is related to this frequency factor A times the exponential e to the negative activation energy divided by RT. The R that we're using here is the energy R, 8.314 joule per mole Kelvin. And then just make sure your temperature is also in Kelvin and your energy is in joules, so this all cancels out. This exponential is fine and all. It still works just fine. But we like, in this chapter, to make everything look like a line. So how do we do that? Well, what they do is we can take the natural log of this whole reaction. And so if we take the natural log, I'll just do this here, of both sides. And keep in mind, this is a reaction or an equation you need to know. But if we take the natural log of both sides, what we get is natural log of the rate constant equals the natural log of A times E gets split apart by adding. So I'm going to do the exponential first. So the natural log of an exponential is just, that cancels it out. So we get negative activation energy over R. And I'm just going to write 1 over T here. Just notice I'm just putting all of this out front. And then plus natural log of our frequency factor. So if you notice, this kind of looks like a linear equation. So we have y equals mx plus b. So in this case, if you were to plot the natural log of all of your rate constants versus 1 over temperature, you'll get a line where the slope here is equal to negative activation energy divided by R. So if you plot this for a reaction, you take a bunch of different measurements at a bunch of different temperatures, and you've graphed the natural log of the rate constant that you found over 1 over temperature. You plot it, whatever slope you get, you'll just say that's a number. So you'll just multiply your slope by negative r to get the activation energy. So you have some of these problems in your book that you'll be plotting, and somewhere you'll just be given the slope. So all you'll have to do is multiply it by a negative r to get activation energy. When you only have 2 points, there's just it's like somewhat helpful of a relationship that you could use. This works if you have more than 2 points, but we'll do natural log of K1 over K2 equals activation energy over R times 1 over temperature 2 minus 1 over temperature 1. And I want you to keep in mind, you can't just combine these two temperatures. You can't not do, so don't do 1 over T1 minus T2. Like, that doesn't work. Don't do that. You want to take the inverse of your temperatures and subtract those numbers from each other. Okay, so don't do that. Then whatever you get for that, you'll multiply by a negative EA over R. Anyway, you can do that to solve for whatever unknown you don't have. Generally, you're trying to solve for activation energy. This is one way to do it if you only have 2 points. And you do have at least one problem in the homework where you have to do that. Okay, in this problem, we're going to have to do it in class. You do need to have Excel or Google Sheets open so you can do this problem. What you'll want to do, so we want to calculate the activation energy. And notice we have temperature and rate constants for this reaction. So in this case, you can make 2 new columns, one that's 1 over temperature and one that's the natural log of K. And you'll get these values. You'll get 4 values here for each of those. Then you'll plot this, where this is your Y and this is your X. So your independent variable is 1 over temperature and your dependent variable is natural log of the rate constant. When you plot that, you will get something that looks like that. You'll then want to find the trend line. If you can't figure out, if you're not very familiar with Google Sheets or Excel, just do a quick search in a browser to find out how to find the trend line. It's not very tricky, and it's a good skill to be familiar with using these documents, the software system. So what you'll do is you'll have plotted natural log of K versus 1 over temperature, and you'll get a slope. Whatever that slope is, whatever that number is, you're going to set equal to negative EA over R. So we're going to solve for EA, so we'll just do R, negative RM equals activation energy. So you'll just multiply your slope by negative R to get that number. So when I did this, I was able to find from the slope that our slope was negative 19,050. So when we multiply that by negative R, we get our activation energy to be equal to 158,381. And that would be in joules. So we could divide by 1,000 to turn it into kilojoules. I don't think we need to do that right now, but just fun facts. You could also then, it says, what's the value of the rate constant at 300 Kelvin? Well, whatever you happen to do for your slope here, you can then plug into your equation. Or you could use that second equation that I showed you with 2 points. Use this as 1 point, use any of these really as 1 point, and then use the temperature as another. So let's do that together. Okay, so we have ln of K1 over K2. So I'll just do K1, we don't know what that is, and K2 I'll just put as the first one. So 2.52 times 10 to the negative 5th. Okay, that equals EA over R times 1 over the first temperature 2. Now that is the temperature used for our first point. So we'll do 1 over, then make sure that's in Kelvin. So that is 462.85 minus 1 over our temperature we care about now. That would be either T1 or, in this case, it'll be T1 since we were trying to find K1. So 430 Kelvin, already in Kelvin. That is nice. So now we're just going to plug in the activation energy that we got earlier, divided by R, times by this whole value. And what we get is the ln of K1 over, or K2, I'm not going to write the number. That's the 2.52 times 10 to the negative 5th, equals negative 3.14. So now we need to get K1 by itself. So we're going to get rid of the natural log, we're going to E the whole thing. So that gets rid of the natural log. And then we can now multiply by K2. So we get K1, which we're trying to find, is 2.52 times 10 to the negative 5th times e to the negative 3.14, which gives us a value of 1.09 times 10 to the negative 6. So now we want to just do a little check. Does that make sense? Well, 430 Kelvin is less than our 462 Kelvin, and so we should have a smaller rate constant, and we do, so it works out. So sorry, there's a lot of steps in here. Then it wants to know, to one significant figure, what is the value for our frequency factor A. But what you could do is on your graph, find the intercept, and remember that the intercept is equal to ln of A. So to get A by itself, so that equals the intercept B. So for our graph, we get an intercept of 30.5. So if we want to get A by itself, we're going to take E times E to the intercept equals A. So E to the 30.5 equals our A, which is 1.76 times 10 to the 13. Okay, very messy, hard to do on one slide, and very much easier to do in a document rather than writing everything down. In this one, we want to, so we have this reaction, and we have a rate constant at this temperature and a rate constant at this temperature. We want to find the activation energy. So I would literally do like 1 and 2 and then temperature and rate constant to try to keep track of them, because that you don't want to mix them up because it doesn't matter. So we get, let's just do temperature 1 is 701 Kelvin, and our K is 2.57. And then we have at 895 Kelvin, we have a rate constant of 567. That's a lot nicer numbers than the last example. So we could use our equation, ln of K1 over K2 equals activation energy over R times 1 over T2 minus 1 over T1. So we'll just plug in ln of K1. So K1 is 2.57 divided by K2 is 567 equals EA, that's what we're trying to find, divided by R, 8.314, times by 1 over T2, 895, minus 1 over T1, 701. So we want to take this whole thing, I got a number for it. The number I got was negative 2.40 times 10 to the negative fifth. And we're going to divide that over here. So divide by 2.40 times 10 to the negative fifth. And we'll do our natural logs of ln of 2.57 divided by 567. And we get our activation energy to be 2.25 times 10 to the fifth. That's in joules per mole. Since I want it in kilojoules, we'll just divide by 1,000. So we get 225 kilojoules per mole. Okay, you survived the math. We're done with all of the hard math for the chapter. Now we're going into talking about mechanisms. So kinetics tells us what happens, and that's our rate law. But our theory for these rate laws, these are called mechanisms. So remember that theories are a way that humans have developed to explain laws. And so what we have kind of come up with is that mechanisms are a series of stepwise reactions that show how our reactants turn into products. So this could all happen in one step or through a few different steps, and each of those single steps is called an elementary reaction. So we have different names for each type of elementary reaction. When we just have one molecule involved in a reaction, in a step, it's called unimolecular. And bimolecular would be 2, termolecular would be 3, and those either can be 2 of the same molecules or of different molecules. And when we have these elementary reactions, the way that the mechanisms have been developed is that our elementary reactions are what help describe our rate laws. So again, rate laws are determined experimentally, and it's something we observe from what happens, and it happens all the time. It's consistent. But our elementary reactions are what we are kind of theorizing happened behind the scenes that we can't really see because it all happens so fast. So it tells us how many molecules, sorry, that's really hard to see, are involved in a step. Okay, now you have to think about, with one molecule, that could be like a molecule breaking apart. Okay, that seems reasonable that could happen. Bimolecular means 2 molecules have to come together in exactly the right orientation with enough energy for the reaction to happen. And that also seems reasonable. Termolecular, though, means that 3 molecules all have to collide exactly in the right orientation with the right amount of energy to go over the activation energy bump. So those are very unlikely. They rarely occur, and most reactions are going to be made up of unimolecular, and bimolecular, unimolecular and bimolecular steps. And so if you see something that looks like 3 reactants going in, so that could be like 2A plus B forms C, that is very likely not going to be happening in a single elementary reaction, but rather made up of a few different steps that are bi or unimolecular. So a prediction or a mechanism for the conversion of ozone, O3, to go into O2. And so the stoichiometry is 2 ozones form 3 oxygens. A mechanism says that maybe 1 ozone converts into ozone and an oxygen atom. And then in a second step, another ozone reacts with that oxygen atom to form 2 oxygen molecules. So describe the molecularity of each elementary step. Well, in this first step, we have 1 molecule, so that would be unimolecular. And in the second step, we have 2, so it's bimolecular. So the reaction for this overall reaction, so we're going to add up what's happening. It's kind of similar to what we did in Hess's law. Okay, so we have ozone going to O2 plus O, and then ozone plus oxygen going to 2O2. So we have oxygens on both sides. So those are going to cross out because they're going to cancel. And then we have our 2 ozones here. So we're going to add them up. None on the other side. And then an oxygen here and 2 oxygens here. So that would go to 3 oxygens. And that is consistent with the reaction we know. And identify the intermediates. Intermediates are the ones that show up on both sides and cancel out. So our intermediate is going to be oxygen atom gas. Here we have a reaction. We have this molybdenum hexacarbonyl plus this trimethylphosphine to make this big old complex and 1 carbon monoxide coming out. So a mechanism that was developed is this one. So we have to determine, is this consistent with the end reaction that we actually do see? So we want to add them up. Now, we have a reactant, so unimolecular there. Only 1 molecule going in. And then we have molybdenum pentacarbonyl and carbon monoxide. That's step 1. And then we have that pentacarbonyl and our trimethylphosphine, creating our big old molecule. So our intermediate, which is for C, is this pentacarbonyl. It's not involved in our overall reaction, so we can cancel it out. So that is our intermediate. And then, and since this involves 2 steps, then this would be unimolecular and this would be bimolecular. And then our overall reaction, since our intermediates canceled out, we have molybdenum hexacarbonyl, check. We have a trimethylphosphine, check. And we have our big old complex with a carbon monoxide. So yes, it does check out. So we use our mechanisms to help us explain the rate law. But all reactions don't happen at the same rate within a mechanism. So when we have a reaction that is slow, it's what's going to really limit the overall reaction. So we call the slowest step our rate determining step. So in order for our mechanism to be kind of like legit, then each of the elementary steps need to add up to the overall equation or overall reaction. Stoichiometry must be in check. They must balance. Each of the steps must balance within themselves, right? So the stoichiometry of each mechanism has to work out. All the intermediates must get used up, and any catalyst we use at the beginning needs to come out. We'll talk about catalysts again soon. And then the rate law that we come from the rate determining step. So the rate law comes from the slow step. Okay, that's how they've developed these mechanisms. And that has to be in line with the experimentally determined rate law. Okay, because that's how they're all determined anyway. So our mechanism basically comes from, or our mechanism needs to work that the slow step predicts the rate law that we got from an experiment. So let's practice. So we have this reaction here, and from an experiment, they determined that this was the rate law. It's the second order with respect to nitrogen dioxide. So as we said earlier, the slow step is what should predict the rate law. So if the first step is the slow step, then the rate law, or then the mechanism with the slow step should look something like 2 nitrogen monoxides or nitrogen dioxides reacting if that step happens to be slow, because that would give us a rate law of nitrogen dioxide squared. So one of the possible mechanisms could be nitrogen dioxide plus nitrogen dioxide goes to nitrogen monoxide plus nitrogen trioxide. How do we know? We don't. It's just a mechanism trying to explain what we see with our rate law. So if we, but since we don't see NO3 in the stoichiometry, that's going to be our intermediate that we're predicting happens. So now the next step, okay, we had a reaction. Now we have these guys. we need to use up our intermediate. And we haven't used carbon monoxide yet. So let's now, so this was step 1. For step 2, and then this was slow, right? Because this needs to predict that with stoichiometry. I know, we said it doesn't, but with mechanisms, it does. Now we have nitrogen trioxide plus carbon monoxide. So we needed to get rid of carbon, or this intermediate, and we need to use our other reactant. And that's going to produce nitrogen monoxide, dioxide, plus carbon dioxide. So, and then this would have to be, if the other one's a slow step, well, this is relatively fast then. How fast? I don't know. It doesn't matter. Just they're relative to each other. So we need to make sure that each of the steps, one, stoichiometry works out for both of them. All of the atoms add up. Our intermediate gets used up, and so it's not involved. We have 2 nitrogen dioxides, but one of them gets canceled on this side. So we have 1 nitrogen dioxide, 1 nitrogen monoxide, 1 carbon dioxide, 1 carbon monoxide. So it does work out. So this mechanism is possible. Is it for real? I don't know. But it is something that could explain what's going on. So let's just talk about intermediates right now. Intermediate, they are not reactants or products. They're also not the transition state. Transition states are super unstable. They're kind of this in-between transition states, assuming that it's not all happening at once. So we have the activation energy, and it settles down. And then we have another little activation barrier to get from the intermediate into the final products, and then it settles down. They are stable. So sometimes, in some reactions that aren't super, super quick, and in some reactions that makes this allowed, they can isolate and then identify an intermediate. So this can help to validate whether a mechanism is true, if it really is what's happening. Also notice that in this case, the way it's written, the first step is it has the highest activation energy. So the way that this plot is made, the first step would be the slow step, and then the second step would be faster because the activation energy is much smaller. So this is how we can visualize those slow steps and fast steps. For something that, which we're going to talk about in just a sec, has a slow second step, it might look like something like this, and then a large second step. So I'll talk a little bit more about that in a minute. Now we're going to focus on what happens in a mechanism that has a fast initial step. So if we look at the rate law for this reaction, where we have 2 nitrogen monoxides react with bromine to produce this nitrosyl bromide compound, the rate law that's determined experimentally is that the rate is equal to K times the concentration of nitrogen monoxide squared and bromine to the first power. Now, if this was a one-step reaction where the first step was the slow step, then that would mean that it would be termolecular because of this one having basically an order of 3 for this reaction. But since those are so uncommon, it's likely that this is a multi-step reaction where the first step is fast and the second step is slow. So in this case, it's like I showed you earlier on the last slide where we have a fast step and then a slow step, so a big activation energy. So what happens in here is we get a lot of molecules that are able to get over that first energy bump, and then they're kind of stuck at this low part, and they have to wait. It's kind of like a backlog where they have to wait for molecules to get enough energy to overcome the second step. So for this reaction, a first step for this could be that we have nitrogen monoxide plus bromine make a an intermediate of NOBr2. And this step is that fast step. So a lot of these intermediates get formed. Then the slow step is where that intermediate reacts with a nitrogen monoxide molecule to make our product, where we get 2 of these nitrosylbromide compounds. And this is a slow step. So the rate of the reaction depends on the slow step. So that would mean that our rate law, we rate the rate law for the slow step, it would be K2, we'll say, for the second step, okay, K1 and K2, times by our reactant at the second step. But what is this intermediate? How can we find it? Well, we can't just, it's not an actual molecule that we're putting in, and so we need to be able to rearrange the equation for that molecule. So what can happen is with this intermediate, so let's go back to our energy diagram. So when we form our intermediate, NOBr2, it's right here, it can either react with another nitrogen monoxide and go over the bump and form our products, or it can actually go backwards and form nitrogen monoxide and bromine. And it's actually going to do both. Since this the first step is fast, that energy bump is really small. So what we actually get is that the molecules can go backwards and forwards, and eventually they're going to reach equilibrium, or they're going to get to the same step. So for equilibrium, the rate forward equals the rate reversed. So the forward rate in this first step is going to be equal to the reverse rate. So they're going to be happening simultaneously. So what we can do is solve for our forward rate. So if we look at this reaction, I'm just going to write that first step again. So the first step is nitrogen monoxide plus bromine, make our intermediate. Since this is a fast state and we get a big population of the intermediate, now it can go backwards. So we're going to have the forward rate, which is going to be equal to K1. 1 will be the forward, K negative 1 will be the reverse reaction, times our nitrogen monoxide and bromine. That is equal to our reverse rate, which is our intermediate's the reactant. So now what we can do is solve for this guy, get it all by itself by dividing by K negative 1. So we're going to solve for our intermediate to plug in to our last slide where we didn't have it. So before we had rate equals K2 times NO and NOBr2. So now we're going to plug in all of this into our into our intermediate spot. So we'll get K2 times K1 over K negative 1 times NO times Br2 and multiplied by this original NO here. So we get, it simplifies, we just are going to simplify all of these K's into one K. We have these two nitrogen monoxide concentrations, so that gets squared, times by bromine. So notice this is what we got for the observed rate loss. So this mechanism where the first step is fast and the second step is slow is one where it does give us the rate law. So So whenever the first step is fast and the second step is slow, we use this equilibrium up here of the first step to solve for the intermediate and then plug that back into the slow step rate law. So let's look at this reaction here. So it says, okay, if this reaction happened in a single elementary step, predict its rate law. So if the mechanism was a single step, then this would be, we have two molecules, it would be bimolecular. And then the rate law would be the rate equals K times hydrogen to the first because of the stoichiometry times bromine to the first, again because of stoichiometry. Remember, this would need to align with what we would find experimentally. So if this happened in a single elementary reaction, this is what it should be. Note, this is actually not the reaction rate law. It happens to have a different order. But so this tells us that this is not really what's happening because it doesn't agree with the experimental results. Okay, in this reaction here, it's the same one. We have 2 nitrogen monoxide plus bromine goes to nitrosyl bromide. Write the rate law for the reaction assuming it involves a single elementary reaction. And is it likely? So again, if it happened in a single step, we know we have 2 molecules plus 1 molecule, so it would be termolecular. Now, is that common? No, so it's unlikely. So it would be, though, if it did happen, it would be nitrogen monoxide squared times bromine to the first power. Now that is what the rate law happens to be experimentally, but not because it's termolecular. So it probably does not, well, it doesn't happen in a single step. Okay, we have this reaction here where nitrous oxide is believed to occur by this 2-step mechanism. So we have nitrous oxide decomposes into nitrogen and oxygen atom, and then nitrogen monoxide plus an oxygen atom reacts to form nitrogen and oxygen. So what's the overall reaction? So let's identify our intermediate here is oxygen. So that's going to go away. So we're going to add up everything on the left side and then add up everything on the right side. So we have 2 nitrous oxide goes to 2 nitrogens plus an oxygen. Does that work out like with stoichiometry? Yes, it's balanced. We don't have any intermediates there, so it looks legit. Write the rate law for the overall reaction. So we're going to write the rate law based off the slow step. It should agree with the slow step. So our rate law is going to be rate equals K times N2O to the first because of this. So we look at the slow step, look at the reactants, and write our rate law based off that and the stoichiometry. So we would need to experimentally determine if this was a rate law, and if so, then this could be a possible mechanism. One thing that could be done is an experiment to try to isolate oxygen atom to see if that's possible, if that's really what's going on. Now I have a reaction. Ozone reacts with nitrogen dioxide to produce dinitrogen pentoxide and oxygen. This is the proposed mechanism. The experimental rate law is K times ozone multiplied by nitrogen dioxide. What can you say about the relative rates? Okay, so we're going to look and see if the first step is slow. That would mean that this, the rate law would need to agree with that slow step. So if we look, here is the first step. Ozone to the first with a 1, nitrogen dioxide to the 1. So it looks like that agrees with the experimental rate law. So that would have to mean that this has to be the slow step, and this therefore is the fast step. In this case, we have another idea of how 2 nitrogen monoxides and bromine react to form nitrosyl bromide. So here's a second rate law that is proposed. So we know that experimentally the rate law, as was noted earlier, is K times nitrogen monoxide squared times bromine. So we need something that will agree with that. So if we look at the first step, that's fast. So we need to write the rate law based off the slow step. So rate equals K2 times dinitrogen dioxide and bromine. Okay, cool. Well, what is this guy? It's not one of our reagents. So it's an intermediate. So we need to solve for that using the first step. Now we're at equilibrium in the first step because it's fast. So we're going to write the forward rate for the first step equals the reverse rate. So we're going to have K1 times nitrogen monoxide squared equals K negative 1 times the dinitrogen dioxide. And then we're going to solve for the intermediate since that's something we want to get rid of. So divide by K negative 1. Plug this whole thing in for that. So we get rate equals, I'm actually going to put this down below, rate equals K2 times, plug in for this one, K1, K negative 1 times and nitrogen monoxide squared times by bromine. We'll simplify those K's together. So the rate equals K times nitrogen monoxide squared and bromine to the first power. So this does align with the experimental rate law. So this mechanism is consistent with the experimental results. So notice we've already done a separate mechanism, so this one could also work. Another thing that could be done is check to see if this intermediate can be isolated, so if they could determine whether the intermediate was this one versus the other intermediate, the NOBr2, that would help us to know which mechanism is actually really happening. Now, a quick comment I want to make is you as first year chemistry students are not expected to ever come up with a mechanism. That is something that you do when you're like a professional chemist and you're trying to determine what's going on in your studies. Now, you as chemists need to be able to look at a mechanism, see if it's legit by determining, does the rate law that is mentioned agree with experimental results? Does it all add up? Does it follow all of those proposed requirements? Or I might ask you, based off of the rate law and these mechanisms, which step is slow and which is fast? Those are the kinds of questions you're asked. You will not be asked to solve for what is the mechanism steps. That's too far advanced, and but you should be able to look at proposed mechanisms and determine either if it's legit or which step is the fast and slow one. The last thing we're going to talk about is catalysts. Now, catalysts are used because they speed up the rate of reaction by decreasing the activation energy. So the way they do that is they change the mechanism for the reaction to make it easier for the reaction to happen. So here we see this catalyzed reaction where hydrogen peroxide decomposes. If you use hydrobromic acid, then it helps this mechanism take place a lot faster because it gives it different steps to take. So notice the first step was it's bimolecular because two molecules are in there. Now that it's a two-step mechanism, and so it can happen with a lot less energy. There are three different types: homogeneous catalysts, heterogeneous catalysts, and enzymes that we're going to talk about. Homogeneous catalysts are in the same phase as the reaction is taking place. So here we have this hydrogen peroxide thing again, and then we add some bromine. Actually, we add hydrobromic acid, and a reaction takes place. And this happens because they're going to be dissolved in the same solvent. In a heterogeneous catalyst, catalysts are in different phases than the reactants. Generally, those are solids that are used as a catalyst, and then liquids or gases are passed over them. So the rate-limiting step happens to just be the absorption of the reactant onto the catalyst. And then once they're on there, they just have to diffuse around the catalyst surface until they meet up, and then the reaction can take place and they can be removed. So an example of this is the catalytic converter in your car, where they take some of these toxic pollutants that are emitted when fuel is burned and get converted into more harmless gases via the catalytic converter. So the gas passes through it, adsorbs onto the surface, a reaction takes place that releases things like nitrogen gas and water and carbon dioxide, rather than carbon monoxide is really dangerous and stuff like that. And then lastly, enzymes. These are biological catalysts. The way that these work is there is a binding site. So here's our enzyme. There's the active site or the binding site where the molecule, the substrate, these are our reactants, are going to bind to. And then once they're there, the enzyme allows for either the substrate to take a certain shape or have a chemical reaction where the products are produced, and this wouldn't happen without the enzyme. So let me just write active site here. The lock and key model kind of says that the substrates fit perfectly into the enzyme, much like a key into a lock. And so these enzymes are specific to this one type of reaction, and other substrates won't be able to bind because they don't fit that reaction. So they are very specific to the substrates and that type of reactant. There are inhibitors that you maybe have heard of, which inhibit the enzyme by either binding into the active site or by binding on a different part of their enzyme, and then it kind of inactivates the active site by changing its shape. So enzymes, they're pretty cool. And then we have this example here, again, an enzyme used in lots of things, apparently ground beef liver as well as potatoes, helps to convert hydrogen peroxide into water and oxygen. So that's a pretty cool way, another way, more biological way for hydrogen peroxide to be decomposed. Now the homework for this assignment is I'm going to extend it by an extra day, so it'll be due on Saturday, so you have a little bit more time. There are 70 minutes worth of questions on average, but unless you want to do the extra credit, and then that will take an extra 15 minutes or so, but the required problems should take about 70 minutes, give or take. So let me know if you have any questions, and then we will move on to equilibrium.